Okay, so we are going to start section 3.2 during this video, and 3.2 is about measures of dispersion. Okay, overall for this section, there are going to be 5 different objectives, and it's going to take us a while to get through them. So this video is only going to cover objective 1 and objective 2, and then we're going to do 3, 4, and 5 during class tomorrow. Okay, so to order food at McDonald's restaurant, one must choose from multiple lines. While waiting at Wendy's restaurant, one enters a single line. The following data represents the wait time in minutes in line for a simple random sample of 30 customers at each restaurant during the lunch hour. For each sample, answer the following. And you're going to see this data on the next slide. Okay, but we're going to answer, what was the mean wait time? We're going to draw a relative frequency histogram of each restaurant's wait time, and then which restaurant's wait time appears more dispersed, and which line would you prefer to wait in, and why. So here are our wait times at Wendy's and our wait time at McDonald's, and again, Part A is going to be to find the mean of that data. Again, you have the ability to pause this video and find that mean on your own for each. Again, when you're finding the mean, you're adding up all of your wait times and you're dividing by the number of wait times there are. There's 30 wait times for each, just so you know. Okay. So the mean wait time at Wendy's, when you add all those numbers together on the previous slide, you should get an answer of 4172. And when you take that and divide that by 30, you should get an answer of 1.390667. The wait time at McDonald's, when you add up all of those wait times, it should come out to 41.59. And then when you divide that by 30, that one's going to come out to 1.3863. So if I were to round these both to the nearest 100, the wait time for Wendy's is going to be 1.39, and the wait time at McDonald's is also 1.39. Okay, so the mean wait time for both these restaurants is 1.39 minutes. Okay, for part B, we're going to draw a relative frequency histogram, and I've drawn them already for you. We've done that already, and that's not the point of this section. We're going to use that to look at the graph though. So here's the picture of what it looks like. Okay, here's your relative frequency histogram for each restaurant's wait time. And it says which restaurant's wait time appears more dispersed. Okay, which line would you prefer to wait in and why? Okay, which one is more dispersed? It's going to be this McDonald's one. When you're looking for the one that's more dispersed, you're looking for the one that's more uniform, that doesn't vary as much. Okay, this has a lot of high bars and then up, down, up, down. This one, except for this one bar right here, this one's pretty consistent over here. So this is the one that's more dispersed. And in general, you always want to, statistically, which line would you prefer to wait in? You always want to wait in the one that's more dispersed. So McDonald's is the one that you'd rather wait in. So McDonald's is more dispersed, and you'd rather wait there. Okay. So now we're really into our objectives here, and objective number 1 is going to be to determine the range of a variable from raw data. Okay, and the range of a variable is the difference between the largest data value and the smallest data values. Okay, or in other words, range R, largest data value minus the smallest data value. That is it. It is not that, there's nothing that's going to be odd about this. It's just the highest value minus the lowest value. So the following data represent the travel times in minutes to work for all 7 employees of a startup web development company. Find the range. Okay. So the range, your highest data value here is 43. Your lowest data value is 5. Range always must be a positive value. Again, it is always the highest minus the lowest. So 43 minus 5. Okay. Highest minus the lowest. Never, ever, ever flip it around. And when you do that, you should get 38 minutes. So your range there is 38 minutes. So really, that's as much as you need to know for the range. Again, highest minus lowest. That's it. And objective 2 is actually going to take us a few minutes to get through. Again, the power of you watching this video is that you have the ability to pause and double check everything inside the calculator. You need to make sure that you're getting the same answers that I am, because eventually I'm going to ask you to do a problem on your own that's going to look like what you see. Okay, so objective number 2 is to determine the standard deviation of a variable from raw data. Now, if you were in algebra last year, the year before, you used your calculator to find this information, and in some instances, you are going to be able to do that. And inside your calculator, we had the ones that were your sample deviation and your population deviation. Those are definitely going to come back into play. But this is college level statistics. We're actually going to find some of these by hand. So the population standard deviation of a variable is the square root of the sum of squared deviations about the population mean divided by the number of observations in the population n. That is, it is the square root of the mean of the squared deviations about the population mean. Crystal clear what that is, correct? Okay, and the population standard deviation symbolically is represented by this sigma over here. Okay, that's the lowercase Greek sigma. Okay, and again, inside the calculator, then you'd be looking for that one inside your calculator. Okay, but again, our goal right now is to do it by hand. You can always use your calculator to check, but we're doing it by hand. Okay, now all this mess in words, you're going to see on the next slide as an actual formula. So the formula, sigma equals the square root of x1 minus mu, remember mu is the mean, squared, plus x2 minus mu, again mu is the mean, squared, so on and so forth, divided by n, and then the square root. Or again, this is the real formula that we're going to use. It's the sum, again this symbol right here is the sum. So it's the sum of your x's minus the mean squared divided by the population. Okay, you do not need to memorize this formula. Okay, you do not need to memorize it. However, you do need to be able to use it. Okay, so again, you can't just stick it into the calculator. You're going to have to do what we're doing again on the next 2 slides. Okay. Another formula that is equivalent to the one on the previous slide is called the computational formula for determining the population standard deviation. And we're missing a sign here. There's a minus there. And a sum. That's the summation symbol in front. Okay, so, and a sigma. So sigma is going to equal the square root of the sums of your x squareds minus, this is an x squared again, divided by n, all divided by n. Again, you do not need to memorize this. Okay, you just have to know how to use it. So again, you can always look it up. You'll be able to write it down, and you just need to know how to plug the information in. Okay, so the following data represent the travel time in minutes to work for all 7 employees of a startup web development company. Same 7 that we were looking at in the beginning. Okay, and we're going to compute the population standard deviation of this data. So with the formula that we're going to use here, should be on the next slide, but just in case, we're going to use that sigma equals the square root of the sum of your x's minus mu minus the mean divided by 2 all over n. So that's the formula that we're going to use. So the first thing we did was find the mean. Again, to find the mean, you're just adding up all 7 numbers and then dividing by 7, and this is what you should get. So mu, the mean, is 24.85714. We found it before, but again, if you need to pause the video and re-find it, you can. Okay, and now here we're going to have our chart. Okay, so all of our x values, this x sub I, is just the 7 numbers listed straight down that were on the previous slide. So we got a 23, a 36, a 23, an 18, a 5, a 26, and a 43. That was just our raw data. Now the mu for this column, literally all I did was take that mean and bring it over and write it straight down all 7 times. So for our next column, we're subtracting. You're literally taking the left column and subtracting out that right column. So when you do that in subtraction for the first one, 23 minus 24.85714 is going to give you an answer of negative 1.85714. Okay, and then so that's literally all you're going to do. You're going straight down the left column and subtracting out that right column straight down. Okay, and then to get this column, literally all you are doing is taking this previous column that I'm putting the asterisk above and then squaring it. Okay, and again, for that first one, when you square negative 1.85714, you should get an answer of 3.44898. The next slide has my chart completed. Again, I would take a second. I would complete this chart on your own before you go to that next slide. And again, something that's missing here on the bottom, this is the sum of your x's minus mu squared. So to get this bottom piece, literally all you're doing is adding straight down that last column to get that number on the bottom. Okay, so this is what your completed slide should end up looking like here. Okay, and again, I don't know why the PowerPoint isn't bringing in all the symbols perfectly here, but this would be the sum of x sub I minus mu squared equals. Okay, so when you add straight down this last column, that's the answer that you should get. Okay, and then, sorry, the answer's popping up right away here. Okay, again, missing a couple things, not translating from the computer to the iPad. So sigma, again, the sum of your x's minus mu squared all over n. So literally now all I'm going to do is take this and plug in the information from the chart. Okay, again, here's that 902,857. That was from right there. That was the sum of all those squared terms. This 7 on the bottom, again, is coming from the fact that there's 1, 2, 3, 4, 5, 6, 7 data values. Okay, and when you divide first. I don't have a calculator up right now. I skipped that step, but you're going to divide 902.8751, divide it by 7, then take the square root. And the answer that you should get then is 11.36. Again, please make sure that you check your work against mine and make sure you're getting the same answers that I did. So now we're going to use the computational formula, and you're going to see that you're going to end up getting the same result as before. So we're going to have our same group of data. The only difference is we're going to be using that formula this time. Okay. So again, what I'm going to do first is I need to find first thing I'm going to find is my squareds here. And then I'm going to add straight down that column to find what the sum of all those squareds are. Okay, and on this side, we need the sum of x's. Then we're going to square it. Notice that squared is on the outside. So I'm going to have my sum of all my x's here. So again, all I'm doing is adding straight down this column to get this answer right here. When you do that, you're going to get 174. And then again, you're going to start just squaring your numbers. So if I do 23 squared, you're going to get 529. Okay, you're going to do that straight across. You're just squaring all those numbers and then adding straight down. The next slide has my completed chart. So again, take a second, try it on your own, plug it into the calculator, make sure you're getting the same answers that I am, and that's what you should get. Okay, so the sum of all your x's straight down on the left should be 174. Once you square everything on the right and then add it, you should get 5,288. Okay, so the formula again, can I go back? Let me just write this whole thing in, and then you might have to pause for a second because that'll come back up in a second. So your formula here is going to be the square root of the sum of x squared minus the sum of x sub I squared divided by n, all divided by n. That whole thing is under the square root house. So this should really come down a little bit further. Okay, so again, the sum of your x's squared is this. So I'm going to take out that first part that I underlined there, and I'm putting in 5,288, bringing down that minus sign. And then I need the sum of x1 squared. Well, here's the sum of x1. That was 174. So I'm going to have 174 squared. And then I need to divide just that piece, just that side, not the 5,284 by n. And n was 7. And then I need to divide that entire thing by 7. Okay. Again, please make sure that you are following your order of operations here. When you're doing this, you're going to have to square that 174 first, then divide by 7, then do your subtraction, then divide that whole thing by 7, and then take the square root. And when you do that, you should get an answer of 11.36 minutes, which is exactly what we had gotten on the last slide. Again, be careful of your order of operations here. Use your calculator to help you. Do not try to enter it all at once. Enter it step by step. Again, square the 174, then divide that by 7. Then take the 5,280 and subtract out that entire answer. Then divide that entire answer by 7 and then take the square root. Again, please play along and make sure you're getting the same answer inside of your calculator. Okay, so the sample standard deviation S of a variable is the square root of the sum of the square deviations about the sample mean divided by n minus 1, where n is the sample size. Okay, relatively speaking, it's pretty much the same exact formula, except the only difference is instead of using mu for the mean, you're using x with the bar. Again, that's your sample mean as opposed to your population mean. Okay, and again, so this is the formula that we're going to be using in the end. Be careful of your order of operations again. And once again, you don't need to memorize this. You just need to know how to use it. Okay, so x sub 1, x sub 2, x sub n are all the n observations in the sample. And again, x with the bar is the sample mean. Okay, so a formula that is equivalent to the one on the previous slide, again, is going to be the computational formula. So just like we had a computational formula for the standard deviation, we're going to have the computational formula here for this one as well. Okay, and that is S equals the sum of x squared minus the sum of your x's squared divided by n all over n minus 1. Okay, again, this formula is slightly different than the one on the previous slide, and you do not need to memorize this. Okay, you'll be able to look it up, you'll be given it, whatever, but you do need to be able to look at a problem and be able to answer the question based on that formula. So we call n minus 1 the degrees of freedom because the first n minus 1 observations have freedom to be whatever value they wish. But the nth value has no freedom. It must be whatever value forces the sum of the deviations about the mean to equal 0. Okay, and again, we're going to go ahead and we're going to use those formulas again. So here are the results of a random sample taken for travel time in minutes to work for all 7 employees of the startup company. And again, all I did from those 7 that we keep talking about, I just pulled 3 randomly. So we want to find the sample deviation. Okay. So again, you have this chart. We want to fill it in. And let's see what I have on this slide. I'm going to have to fill some stuff in here. I'm just looking to see what I have. Okay, so your mean. So all I did was take those 3 numbers, 5 plus 26 plus 36 divided by 3. That's how you got the x with the bar. Okay, x sub I was just the list of our 3. And again, all I did was take the mean and put it down that column. Okay. This next column should say x sub 1 minus x with a bar. So again, all you're literally doing is going down that left-hand column and subtracting out the right-hand column. So your first row, you're doing 5 minus 22.33333. That's negative 17.33. There's going to be a completed chart on the next slide. Again, I'm just kind of telling you how to get it here. And again, here, this last column, we're taking the answer that we just got here, and now we're just squaring it. So literally, you're taking that negative 17.33333 and squaring it, and when you do that, you should get 300.432889. Okay, and then your bottom here should say the sum. That's a sum, sorry. The sum of x minus x bar squared. Okay, and let me see what's on the next slide. I might have to fill some stuff in here. Oh, here's our formula. Again, equals the sum. I'm going to write what this is. Again, there is a completed chart on the next slide, but let me just write in what you have here in case for some reason it's a little wacky. So when you find the sum of this column right here, it should end up being 500.66667, and n minus 1, n is 3. You had 3 data values, so you're going to have 3 minus 1 on the bottom. Okay, so again, here's that completed chart. And again, let me just fill in the pieces that are missing here. And again, when we do that, this was what I had plugged in on the last slide. That's the sum minus. And then again, I had 3 minus 1 on the last slide here. You see 3 minus 1 is 2. So when you divide that 500.66667, divide that by 2 first, then take the square root of that answer, and you should get an answer of 15.82 minutes. Okay, and then we're going to do the same thing that we did with that original problem. We're going to do the computational formula. And again, you're going to see that you get the same exact answer. So we want to use the computational formula, and you'll see that it's going to yield their same result. So again, the first thing I need to do is my x's squared. Again, same 3 that I just sampled in the last one. So literally all I'm doing is taking 5 and squaring it. Okay, and then again, we're going to add down this column to get this answer, and add down this column to get that answer. Okay, there is a completed chart on the next slide as well. And the formula here is that. Okay. So your computational formula, again, when I squared everything, these were the results I get. When you add down the left column, you get 67. When you add down the right column, you're going to get 1997. So your sum of xi minus the sum squared over n divided by n minus 1. So again, the sum of your x's squared comes from here, 1997. So I just took that in and plugged in 1997. Okay, then over, I can't change the color of my pen. Over here, the sum of your x's is 67. So I'm going to have 67 squared. Regular old n, you had 3 observations. So I took out that n and plugged in 3. And then on the bottom, I did n minus 1, or 3 minus 1. Again, follow your order of operations. You have to square first, then divide by 3, then do the subtraction on the top, then divide, then take the square root. Again, please make sure that you're playing along. You should be getting an answer of 15.82. Okay, and then for our next one, we want to determine the standard deviation waiting time for Wendy's and McDonald's, and which one is larger and why. Okay, and to do that, I am going to show you how to do that inside the calculator, but I think I might make a separate video of that because I think this is getting a little long right now. So I might do a separate shorter video. So again, I'm going to show you how to do it in the calculator, but let me just get you your answers and then we'll get everything in the calculator. Okay, so determine the sample standard deviation for Wendy's and McDonald's. When you do that, for Wendy's, you're going to get an answer of 0.738. And for McDonald's, you're going to get 1.265. Again, I'm going to do this inside the calculator in a separate video to show you. Okay, and again, remember from earlier, we said that McDonald's was more dispersed when we looked at that graph. Okay, the same thing here. Look at McDonald's standard deviation. Since McDonald's standard deviation is bigger than Wendy's, that once again means that McDonald's is going to be more dispersed. It has a larger standard deviation. Okay, so I'm going to end this video here. And again, I'm going to go back and do a calculator to show you how I got these two. And when I do that, just keep in mind that it is all this data that I'm going to be entering into the calculator.